Okay, so that was my hometown. So you guys are welcome. If you are around, drop me a note. I would love to show you around. Now,
You have some security conference there?
oh yeah, we have a security conference there. So actually, the CFP is just open. So you could just type C0C0N. Yeah. So okay, I could give you more info if you hit me up later after the talk. All right, so now let's get started. All right. My name is Anto Joseph. I am a security engineer at Intel, and I have been a speaker and trainer at these conferences. My current interests include machine learning, program analysis, and mobile security. So today we are talking about symbolic execution. Have any of you tried doing anything related to symbolic execution? Yeah, I see a hand. Okay, that's it. All right. Okay, 2 people. All right. I'm sure you guys have heard about the Cyber Grand Challenge, right? More people here, I guess. Oh yes. Okay, so it's the world's first all-machine hacking tournament. So exploitation mainly used to be a manual task, like finding a rope chain, exploiting a binary, the way you do a CTF. It's mostly done by humans. The Cyber Grand Challenge proposed this idea of machines doing this, and this happened at DEF CON last year. I was there and I was really happy to see that happening, and one of the teams in the competition, the Selfish team, open sourced one of their tools. It's called angr, and one of the main components of angr is symbolic execution. It's not the only component, but it is one of the main components. And I want to discuss what symbolic execution can do in vulnerability research. How can it better help us to do good stuff, find bugs. That's what I meant by good stuff. Okay, so this is a very simple program. How many of you have used a fuzzer before? Okay. How much long do you think a fuzzer would take to hit the vulnerability over there? If this is the code that has been compiled and I'm just fuzzing it. Give it average of, I don't know. Would a fuzzer figure out that the first condition has to be 1, 2, 3, 4 for it to bypass the first check and then get to the vulnerable endpoint? So today's softwares are really complex, right? We can fuzz all we want, but if we have a simple check, you might not be hitting the right endpoints. So symbolic execution is a way of solving formulas. Let me explain it with an example like this. So let's consider that this is a C program, and you can see that we are modeling small equations and getting answers towards the end. We are not concretely inputting any numbers in there. So let's look at this section, this particular section. So it says if x is greater than 0, x has been confirmed as a plus y. Consider a as a symbolic variable. Okay, and now it adds another constraint, which is x should be greater than 0, so they just say that a plus y is greater than 0. And we traverse all the way, and we can explore all the parts of a program this way. Does it make sense? So instead of just randomly fuzzing, fuzzing might get you somewhere, like maybe here or it's just arbitrary where you get while fuzzing. But with symbolic execution, you can trace all the branches of a program. So here we can specify which endpoint we want to reach, and the symbolic execution engine can craft a formula, something like this, and solve it for us. So, what does that mean? So, we have symbolic execution tools, and these rely on something called as SMT solvers. Z3 is a very famous symbolic execution tool that you could use to solve symbolic equations. So, let me just show you the demo. Okay. Okay, I didn't realize it was not there. Is this visible? Yeah, all right. So, Z3, as I said, is from Microsoft. It's free, and it's an SMT solver. So, what I have written right over here is the SMT language. It's very readable, and it has Python bindings, of course. Here you can see that I am trying to solve a simple equation. The x plus y has to be greater than 5, and x has to be greater than 1, and y has to be greater than 1. So, from the earlier diagram, you could get an idea that something like this would be the result of one of the paths of a program execution. Like, if you consider one path would have such a constraint, and this needs to be solved. So, this is like a problem that should be solved, and the solution will be your input, so that you can reach that particular endpoint. So, let us run this. Okay. Okay, so they just figured out a solution which says y can be 4 and x is equal to 2, and it works out. All right. So, this is very simple, and it works with toy programs like this. So, how do you implement something like this in real world programs? So, we have mainly two popular symbolic execution frameworks. One is angr, of course, from the shell system, and then we have cli. I personally have done some work with cli because I use it for some of my projects. So, I will give you some ideas on how to use cli symbolic virtual machine to find vulnerabilities in functions, simple programs, CTFs, and even whole GNU programs. So, it is going to be a lot of demos, and this stage did not have much love towards demos today. I am just going to try it out. Okay. So, this is a sample program. How many possible outputs does this program have? Anyone? I mean, it's C, it's the kind of oldest language.
Can you increase the font?
Yeah, sure, please. Better?
Yeah.
Oh, fuck. It just keeps on fuck. That's fucked up. Sorry. What? Okay, it went out the directory. Get sign. Should be good, right? What are the possible outcomes of this program? How many outputs does this program have? As in, sorry? Okay, okay. So three outputs, right? Yeah. So let's do this the CLE way and see if we can, let's see how to do it with CLE, basically. Okay. So the first part of doing symbolic execution using CLE is to get the LLVM bit code. How many people are familiar with LLVM here? All right. So it's a compiler tool chain and it's pretty good at what it does. It has very security centric tools like libfuzzer and all that. I suggest you guys explore it. It's a very good fuzzer. And I'm using LLVM. So the LLVM front end for C compilation is called clang. So I'll use clang to compile this particular C file and get the bit code. So this is the bit code file, get sign under .bc. So it's LLVM IR bit code. It's not readable. There is a .ll version that is readable if you want to. And I'll just delete these folders from the last run. Okay. So this is how you would compile the program. So all this happens inside the Docker container that I have. So if you guys want to try this out later, I can upload the Docker containers somewhere and then you can just have all the examples to yourself. So you can just do a history on the terminal and you can get all the commands that I have typed in. So okay, so that generates the bitcode file. Now you use CLE to iterate over it, and the symbolic execution solver that CLE internally uses is called STP. It's different from SED3, but that's something that CLE uses. And we can see that there are 31 instructions that were executed, and the program had 3 parts. So it figured that the program has 3 parts, and the best part is it generates test cases for those 3 parts. So if you see this, these 3 files are the test cases that it generated for those 3 parts. Now let's see what's inside there. So that's a 0. It's a 1. What is this? Okay, let's just check run the program and see what's the exit status. So you can specify okay. So the first one is a 0, as we said. The second one is a higher number. The third number is a negative number. So it generated test cases for all 3 possible parts of that program. Now this is a very simple function. It's not really that scalable and you need the source code for it. So let's do something better. If at any point that you have a doubt, please feel free to stop me. A Mace is a much more complex program. I'll just show you what it is. So this is how the Mace program look like, and you can use the characters WASD. If you have ever played Counter-Strike, you would know, I mean, all the games, right? WASD to move around the maze, and you should figure out what is the right combination of the keys that you have to use to get to the endpoint, which is a pound sign. So, I would try some random keys and see how it works. Okay. All right, I went ahead and I got blocked, so it was a fail. So, can we try to implement CLE here so that it kind of finds the solution for us? That's what we are trying to do. Before that, I will just show you the source code of this program. So, it's a small C program which just use read statements to read input from the keyboard and then just move it accordingly, and this is the maze that's being drawn. Okay. So, let's so what's our goal here? The goal is to reach the success state. How do we tell our symbolic execution program to figure out a path that can get us there? So, in the code, obviously we will add something. This is the section where you basically win. So, I just add an assert statement. An assert statement it just works like like regular C assert statement. So, I added an assert statement here to indicate that this is the section of the code that I have to reach, and I just added the header file for CLE, and then you just compile it to the bit code, and you can see the bit code file here, again using the CLang program, and execute it. Now, CLE. So, it tries out lots of variations by solving the constraints that this particular LLVM bit code had, and it has figured out 309 paths and it generated around 306 test cases. Okay. Now, let us see if we have a winning condition. So, the assert statement makes the program to cause an error. I will explain what that is. Okay, so seems like we have an error, and let us just look at the number of test cases that CLE generated. It's a lot, so that's why I did the. Okay, now let's see what is the input that's causing the error. Okay. So, seems like this is the output input that is causing the error, means this is the input that gets us to the assert statement. Okay. Now, let us just try it out and see if it is okay. Executed the program, pasted in the solution. Oh wow, wow. Exactly. Now, after this, do you really want to test programs like with hand? Do you want to do code reviews, or do you just want to do this? Is this the only possible solution? The thing with CLE is it kind of halts at the first attempt where it is successful. So, we are going to tell it to give us other test cases where it is not. Yep. Okay. So, I just gave it an argument which says emit all errors. So, which makes it try all the possibilities that causes an error condition. And now you can see that it generated 309 test cases. Earlier it was 306. Okay. So, we have 3 more bugs here, I think. Let us see. Okay, so I was right. We have 3 additional inputs that would get us to the winning condition. So, let us test them out. Okay, let us test this one. Okay, this is long, and I think this is the right solution. Let's see how this works out. Okay. Yeah, I guess this is the right one. Oh wow, yeah, I always guess wrong. Okay, now let's okay, I guess this must be it. What? Yeah. I think this should be it. This is really long. Okay. Yeah, I guess this is the one. Yay. So, and there is also one more solution. So, this is all in your Docker container, so you can just try it out. And it's very simple how that I just modified 2 lines in this program, and then I could figure out 3 additional conditions that the programmer didn't intend. Okay? And this is again a toy program. Let us do something CTF level, right. Okay. Which one do I choose? Okay, let us go this way. Okay, this is an NuiDo hack CTF, and there is a write about there. I am just gonna try it out. Okay, so it's an 64-bit ELF executable, and I guess it asks for a password. Let's try something. Okay, that's not it. Now, we don't have the source code for this particular file. So, what do we do? I mean, how do we approach programs that doesn't have source code and we still want to do cleave with it? Any ideas?
You can check the output.
Sorry?
You can check the output of the program, yes?
I mean, how do we get the source code? Because, yeah, exactly. So, what do we use? Yay. Does this look familiar? So, we just loaded the program in IDAPRO, which is the decompiler, and here we just translated the assembly code to C code using the hex race. So it just gives you very readable code. So here you can see that something happens, else try again. So we want this to happen, right? All right. So where do we put the assert statement now? We just put it over there. Okay. This is compilable C code. So that's what you can see here. Yeah. No changes. I just put the CLI assert statement here because this is where good stuff happens, and we don't want to go anywhere here. I just add the CLI.h file here and put in the function body. Copy paste it over here and compile with clang. Obviously, you will get the bit code file. Now I'll run it with CLI. Okay. Now it wants me about something. It's saying calling external printf. So CLI works on LLVM bit code, right? Can it understand what printf is? Because where does printf come from? Anyone? libc, exactly. So we need to have a version of libc that the CLI can instrument. So CLI actually provides you that. It's called ulibc, and you can just specify it. Let's do that. Okay, so now that's sorted. Now it has a warning, and it says the usage is main.bc and then the pass. So it's an argument that you have to give this program. It's a command line argument that you have to provide. So how do we make the command line argument symbolic so that the CLI tries to figure out what exactly needs to be the input? So this, so just add -- sim arg 100. So 100 is just the character size. I don't know what's the number of characters that it takes to get the key. So I just provide an arbitrary number which is 100. It can be 80, whatever that you think it is. So this should be clear now. We provide libc here, and we provide the POSIX environment. So some functions like write are implemented by the operating system. So CLI gives you functionality to execute code which has system calls as well, and then you provide the bit code. And since this bit code takes argument from the command line, I am providing it as a symbolic argument, which can be a 100 characters. So I just give it a go, and oh, I just saw something blink. So this is, I think, was for 200 points. So it's pretty cool that I can solve it on the stage. So we have an assertion fail right here. Let's figure out what this is. Okay, so we have a test case that kind of gets us to that point. Okay, test. Okay, it's Pandi Panda. I don't know if it's a French thing, but yeah. Okay, So, let us try it out and verify if we are right. Okay, I should. Oh yes. So, yeah, we just solved the CTF challenge, no biggie. Now, yeah, this is pretty easy, right? Now, let us do some slides now. I have been doing demos for a while. Right. All right, we covered this. And these are the other symbolic arguments that you could provide. And these are the, it can not just be arguments, it can be files too. And CLE also supports sockets, IPC, etc. So, it is pretty good. And yeah, this is the list. So, UC-libc is a modified version of libc, which CLE can instrument. So, when the control flow transfers from the bit code to something that is a system library, CLE can't really understand what is going on there. So, that is why we have to have something like UC-libc in there, and the same applies for the POSIX runtime as well. Now, I think GNU core utils and bin utils has been the tested software suite ever, because it is easy to compile. You can run all the fuzzers tutorials comes with it. So, it has been pretty tested, and surprisingly the developers of CLE were able to find around 2 to 3 high severity bugs in these tools. So, and this is kind of an indication that that this project is mature enough to actually find production quality bugs. So, let us figure out how to do that. The first part of doing something like that is, how do we compile all these programs with LLVM? Some of them have their own build systems and that might not work together, etc. So, we use something called as WLLVM. So, it is a whole program LLVM which lets you compile entire source packages with LLVM. It's not a magic sword, it works most of the time, and it kind of puts in the LLVM bit code in the binary that it compiles, which you can later extract with a tool that they give called extract BC. So, once you do that, you will have the bit code of the files that you have compiled with LLVM, and then you follow the same steps that you have done before. Okay. So, before we go into the GNU one, it is a bit complex. Let us do a little better one, which is the AIS3 Crack Me. Okay. So, again, this program does not have any source code to it, as in we do not have the source code to it. How do we plan on hacking this? Because this has been kind of obfuscated and the code is little tricky. So, we can't really copy from hex race and then do whatever we did with CLE. So, we will try to use a different tool which is called angr, and I have angr in another Docker container. So, let us try that. Before we try angr, let us understand what this program does. So, have you heard of Radar? It is a free tool, it is pre-installed. You can do similar things with IDA, but then this is totally free. So, okay. So, I just loaded it up, did some basic analysis with it. So, AAA does lots of analysis on the binary, and then AFL prints all the functions in this particular binary, and main is always a good starting point, right. So, we would go to main. and we have the control flow. So, this is like a very nice representation. We know that this is the control flow. We can take the false branch and then it would go here, and then the true branch goes here, and end of the day this is where you want to land, right? This is where you want to land, and this is the false condition. So, take a good note of this, and I will just show you how complex it is to solve this. Yeah. So, we just load, this is a Python script that uses angr, and it's another symbolic execution engine, and this is where you just create a project. It has been heavily commented, so you can get an idea, and this is the one line that it matters. Path group dot explore find 4602. So, that is where the key is. We just tell angr to figure out how to get to this particular offset. Okay? We have no idea about this binary, we do not know what it does. All we saw was a string in the control flow that this is where it is. So, let us run that. Okay, and see, fingers crossed. Oh yes. Okay, that seems like this is the key. Let's okay. Oh yeah, I need to like I need to paste it with the other one. Oh yes. So, we did not have any source code, we did not do any decompilation, all we did was just do a strings, and then we figured that this is where we want to reach. We politely tell angr that please figure out a way. Angr did it for us, and we just paste the CTF in there, CTF key in there, and yeah, get on going. So, do you find this really interesting that I can solve CTF challenges just like that? Isn't that cool? If this isn't cool, what is? And surprisingly, all the demos work. I am surprised. All right. Okay. So, I'm going to push my luck and do this again. Okay. Let's do the example one. This I don't have good successes with it, but then let's give it a try. So, again this we have source code for it, but right now let's try to solve it without using the source code, and we will try in CLE with using the source code. So, we can see both the versions. So, this is again another CTF. I just took all these CTFs from the angr examples directory and just used it for CLE as well. And let's see. Okay, it asks me to go away. It's pretty rude. Now, let's see what's inside sol.py. Okay. This is all these lines are by default. You don't have to bother because this is the angr setup. And if you decompile, let's decompile this. Oh yeah, radar is installed in this thing. Okay, or dot dot. Okay. Okay, there is a main function. Nice. Yeah. Okay. So there is something that's happening with the passwords here. Okay, and then it has a false and a true condition, and then it just gets, it just prints out stuff. So this program just has one false and one true condition, right? So how many path groups does this program can have? It just has 2 branches. It can have 2 path groups. So in angr way of speaking, it has 2 path groups. So that's what you can see here. There is one path group that is the active of 0, and then the other path group which is the active of 1, because this program can only have 2 path groups. Now we just save both the input, the result of these path groups to a variable which is input underscore 0, and then we are just testing if it is the correct one or not. So we'll just execute Python sol.py. I don't even know what's the operation that they are doing, but then I know that this is the key. So sneaky, right? So I didn't know what they are doing. I just know that there are 2 path groups, and just printed out what's in the path groups, and this happens to be the key. Let's just make sure that, okay, I don't know what's the username, but then I'll just give the password. Okay, so there is no username. It was the reverse of Mubix talk. Now let's solve it while we have the source code. Okay. So this is how the source code looks, and apparently it's just a string comparison. Okay, and it does a string comparison, and if accepted, it prints something like welcome to the admin console. So if you have the source code, what is the first thing that you do? Where do you want to reach? Where do you want to reach? Put an assert statement over there, include the header file, then you compile it. It's pretty standard. And here we have inputs. The input is the username and the password. So we have to make, if it was a CTF program, that would take a input from the terminal. You can give it as, you can either give it as symbolic arguments with the -- sim that we did earlier, or we can just modify it right over here. So I'll just modify the program. Oh, okay. I haven't done my slides yet. Yet. _clee.c. So as I said, I just modify the read statements to symbolic arguments. So the username, I made it as symbolic, and the password, I made it as symbolic, because these are the things that I don't know, and it's a good idea to make the things that you don't know as symbolic, so that Clee does the hard work. Okay, and I don't want to go away, so I just don't put the assert statement over there. I want to get the admin console, so that's where I go. I compile it just like you would, and okay. And instead of doing the symbolic arguments, I will just run the bit code, because we have already made those arguments symbolic. So, it would be something like foxware underscore clee dot bc. Okay, so we have lots of go-aways. It's really angry at us. But let me see. Okay, do I see something here? Welcome to the admin console. So, obviously, I would just go ktest tool clee-latest star.err what. Oh yes, okay. So, Clee figured out that key in just 3 tries. So, the first one was something we can look it up, but then on the 3rd try it kind of figured out what is the key. So, that is the best thing about Clee. It's not a brute force solution. It knows what it is doing, and since it was a simple string comparison, it knows that mango equals mango. There is nothing that equals to mango. I really like mango, so I don't know why I said that. Okay, so let's look up what this is. Ktest tool. Okay, so sneaky again. So we solved it with angr, we solved it with Clee, and you found that this is pretty easy to do. This is black magic. So I guess that's all the time I have. Okay, I'll just do some slides. Okay. So what are the limitations of Clee? Path explosion. If we have n number of paths and if we have obfuscation in the binary, the Clee would, it's not a limitation, it's just a restriction that the hardware is imposed because it just takes so much time for Clee to solve everything. So when you are trying this out in CTF or in your products, if you have the source code, try to do it with your source code, or if you don't have the source code, try to single out that particular function which is critical and just try to solve it. Don't try to symbolically execute the whole program. So that's something that we should take care of, because that just adds so much time. Try to minimize the function as much as possible, and don't try to figure out what's the SHA-1 hash of whatever using symbolic execution, because that will take forever. And program dependent efficiency, because if the program happens to take just a single path, the whole point of doing symbolic execution is lost, because it's about taking multiple paths and figuring out the different solutions. The environmental interactions are right now limited to file operations, sockets, IPC, etc. So if you have a program that does something else, that part of the program might not be symbolically executed. So that's something that we have to take care of. And countermeasures. This is something that people keep asking me. So it's not really an attack, it's just a way of doing things. And if you happen to have a license validation in your program, symbolic execution might be something that you should care about. So code obfuscation, and not just jargon, as in you just don't put in jargon code which is dead code, because Clee has this dead code elimination thing. So they'll just skip ahead that dead code. So if you have code that depends upon the input and does some transformations, and then you can make it to use something like a path explosion and make it really difficult for a symbolic execution engine to parse it in limited time. So that's the best you can do, and this is a research paper that talks in much more detail. I don't really have the time to go in detail about that. And Yeah, I guess. Yep. Thank you. So if you have, I think I am running out of time. So if you have any questions, I'll be.